Hello everyone, it's Jason here, and well, welcome to the video that I have today. This is going to be a video taking you through a GCSE maths paper, and it's going to be a higher tier one. As you can see in front of me, I have the one from May 2017. Now, I'm obviously going to do the best I can to ensure I don't make any errors or mistakes. So if I do so though, it'll be arithmetic. But bear in mind, this is a non-calculated paper. It's the only paper out of the three that you would do if you do this exam that would involve no calculator. The other two do have calculators, and I would always advise that if you're ever doing an exam with a calculator, then to use the calculator even if the sums are as basic as 2 plus 2, because you never know, a little error can always slip up, especially under timed conditions. Now, we're obviously going to take longer than the time here, because also, as well as going through it, I'm going to be explaining the methods that you would be using to actually answer each of the questions. Now let's get on with it. So, question one, the first question, as we can see, is a scatter graph, and it says the scatter graph shows the maximum temperature and the number of hours of sunshine in 14 British towns on one day. Immediately, we can already see something going on there. We have this general trend going up, and then we have this here which looks like it's just a bit out of place, so bear that in mind. That could actually be involved in a question. Now we have here maximum temperature. This is the maximum temperature going up to more than, say, 20 degrees, and then we have the number of hours of sunshine going in this direction. That's the x-axis, and it's also the axis in which you have an independent variable, the variable in which we're selecting, and then the dependent variable, which it goes along this y-axis here, which is what's being measured. Okay, so let's see. One of the points is an outlier. Okay, so remember that I referred to here. It says here, write down the coordinates of this point. So to do that, it's not as difficult as it looks. You first start off with the x point. Remember, in a format of coordinates like this, x coordinate goes there and the y coordinate goes there. This is the x-axis here. This one up there, sorry, going vertically, is the y-axis. And we'll go along, and remember, we have to make sure that we pay attention to the actual scale we have. Make sure that you know what it's going up in. This is going up in units of 1 per 5 blocks. So here, where we can actually see where all the line, we're going to have 10. So that tells us the first coordinate here is 10, right? Okay, and then we have to also then do the same test here. Make sure that you know what this is going up in per, say, number of blocks, and we can see again it's actually going up in ones. So this is 11, that is 13, and then we see here if we draw a line. By the way, in the actual exam, you would use a ruler to really do this if you want to be very accurate. I can actually do a straight line like that, say, with my little tool. Pretty impressive. But anyway, it lands us bang on number 19 there. Okay, so then that actually tells us here that at 10 hours of sunshine we record a maximum temperature of 19 degrees, but that means our coordinate here, let me just switch back to blue, our coordinate here will then be 19, like that. Anyway, let me just get rid of this bit there. So that gives us the answer for the first one. Then for all other points, write down the type of correlation. So I said before that there was this general trend we could see where it was going up. This is actually known as positive correlation in maths. That's the actual answer, positive. It's a positive correlation. As the number of sunshine, the number of hours of sunshine is increased, so does the maximum temperature reached in that particular time of day. And that makes sense. Obviously, with more sunshine gives more heat. More heat gives a higher temperature. That makes sense. So that would be the answer. I don't know why it keeps switching me into blue, red. So we'll put the positive. Excuse me. Sorry. Hang on a minute. Hello, hi, sorry, I must apologise for that interruption. There was a phone call that came in. So as I was saying, anyway, we have an instance here of positive correlation, and for some reason it's given me the wrong pen. So here we go, positive. My handwriting isn't great. And even write actually correlation. No, actually it always says correlation there, so you don't need to. But it's positive. Okay, so it says here, next one. On the same day, in another British town, the maximum temperature was 16.4 degrees Celsius. Estimate the number of hours of sunshine in this town on this day. Okay, so I guess for that then we're going to have to use this little scatter graph for that. Now, the idea is is we're trying to work backwards. Remember, this is an estimate, but we're working backwards. From now, what we'll understand is the actual temperature. So that was the dependent variable, and we have a model now. We have a model on the scatter graph of what we can expect a certain number of hours of sunshine to be for a given certain temperature. So what we'll do there is we'll go to 16.4 on the temperature scale here, like that. So we have to take ourselves to 16.4. So and that will be, and again it's giving me red ink. I don't know why is it doing that? So 16.4, and this is important to also note, this is 17. So these blocks are going up in 0.2. That's 0.2, 0.4, 6, 0.8, and then 17. So 16.4 is going to be the second little block in. So that's that one there. I've drawn on. Then the other thing to also note, in order to do this estimation, we need to actually draw a line of best fit. The method for doing that really is, mind you, let me get rid of this here. Delete that because we don't need that for this question. So with the line of best fit, what you want to do is try and draw a line, right? You want to lay your ruler on the actual piece of paper and draw the line, a line that will go through as many points as you can get to go through.
Sunny Ryan.
My apologies, there was another interruption, so getting back to it. Here we have yes, I had on mark here, there, that's 16.4. Now, to draw your line of best fit, you want to basically draw the line for as many points as you can. So my line of best fit would look a bit like that. And then what you want to do is get your ruler and you want to draw a horizontal line going across to the line of best fit, like that. And then you want to descend, do a vertical line, then descending from that. So let's do that here. And that'll be again with your ruler. And then now remember, this is an estimate, so actually even if you don't get the exact answer to the nearest, say, decimal place, it rather doesn't matter because there'll be a bit of a range of error that they'll allow for, but make sure you get it as accurate as you can do regardless. Now, so that's going to be, if we look here, let me get the shape tool off, we can see we've got here, well, as I said, that one there was 12, and again it's really messing about with the pens, so that one there is 12. And that's going to be 12.2 for 6. So let's just say 12.6. I think that's 12.6. So that's 12.6 hours of sunshine. That seems to be all right. So next question. A weatherman says temperatures are higher on days when there is more sunshine. Does the scatter graph support what the weatherman says? Now, the weatherman is basically giving a bit of common sense sort of commentary here. Yes, obviously, if you've got more hours of sunshine, you've got more heat coming off the sun, and then you've got more higher temperatures as a result. In other words, positive correlation. We've already really answered this question. In fact, you're getting a free mark here because you're getting the same question but in a different wording. But let's just put, all you'd need to actually put, basically, and this is funny, you'd put yes, and then write, because there is positive correlation. Dum dum dum, and there's your answer. That will get you the mark. You got the right answer and a good reason. So here we have here express 56 as a product of its prime factors. Now this is all about trying to break down this number 56, such that the numbers that will multiply together will give 56, and those numbers which multiply together are all prime numbers themselves. Okay, and they're the smallest prime numbers in which that it can be broken into. Now, my favourite method for doing this is to break it down as coming from like stemming off from each number. So you'd write 56 like this, and then you'd stem off into two factors. Now these necessarily won't be the prime factors just yet, they'll just be factors, but those factors will also be able to be broken down further. So we could say 8 here, and we could say 7 there. Now we all know that 7 is a prime number, right? It cannot be split up any further other than 1 and 7. And of course, a number that does that is a prime number. But the 8, of course, can be split up further. We could split the 8 into 4 and 2. Here we have a 2 there and a 7 there. So these are already two numbers which are primes, right? 2 cannot be split up into numbers besides 1 and itself. But 4 can be split up further. We have 2 and 2. So, and again, you want to circle your prime numbers, and then we've got another interruption just to for good measure. So circle your prime numbers. We've got 4 prime numbers that make up 56, and you can actually rewrite them out like this. You could say 2 times 2 times 2 times 7, and that will actually equal 56. So, by the way, it's not always a bad idea to multiply all that out to make sure that you get back to the number. And we can actually find a way of writing this more, say, succinctly. That's to make it look more simplified and niche, by writing 2 expressed as a power. We can do this actually by saying that when a number is times by itself, for however many number of times, it's raised to the power of that number of times. In this instance, we have 2 being times by itself 3 times. So you'd actually have 2 to the power of 3, and that'd be multiplied by 7. And that's the most simple way in which you can write that, and then that's your answer, 2 to the power of 3 times 7. Dum dum dum. That's your answer. Then we have here, work out 54.6 times 4.3. So my first way in which I'd advise doing this is first, actually, just multiply through by 100. So times 100. So basically what you're doing actually, you're timesing each component by 10, right, in doing that. That will actually make the numbers easier to work with. So you actually have this instead. Now, bear in mind that was multiplied by 100 to make it easier to work with. So when we get our answer, we're going to have to then divide it again by 100 to go backwards. So that's what we have. Now, I always use the grid method. I think it's the one that lays it all out the easiest. So I'll just take us through that. We have times here. We have 500. Then that's the hundreds column. We have 40 for the tens column, and then we have 3 for the units. Draw a line all the way under that, and then we have 40 here. 40 again. That's the units column for the next one here. And then we have now this is so basic. You might as well be doing key stage 1 at this point, but I'll show you anyway. Let's go down, go down. So firstly, 4 times 5 is 20. Add all the zeros. This is obviously 3 zeros altogether. So we get 20,000, put your little comma there. 4 times 4 is 16. Add 2 zeros, put your little comma there. 3 times 4 is 120. No need for a comma because it's in the hundreds. 3 times 5 is 15. Add the zeros. So that's 1 point, yeah. 4 times 3 is 12. So that's 120. And 3 times 3 is 9. Done. Then what we need to do, we need to add these up along going in this direction. So we have 20,000, that's 1,600, add 120. So let me just make sure so let's work that one from backwards. So we would have 0, 2, 7, 1, so that's 20, and 2, I guess. So that's 21,720. And then we have, going backwards again this way, 9. So again, I'm adding these ones up now. So we have 9, 2, 6, 1. And if you make sure that these are also all in the same columns, then you can also then add them going down. So then we add these ones going down. We have 9, 0 at 9, 2 and 2 is 4, 7 and 6 is 13, so you put the 3, 1 down to carry, 1 add 1 is 3, and then we have 2. So there's your answer. Well, that's not your answer actually, because as I said, we need now to divide that by 100 to actually get, remember this is the decimal point here. We now need to divide by 100, and dividing by 100 moves the decimal point 2 places to the left, right? So you're going to go 1, 2, 1, 2, right? So essentially you've got 23,349 divide by 100, and then that's going to equal 23.49. As you say, that's where the decimal point has gone from. And that's your answer. This is the answer, 233.49. Okay, next question. Now this question, I love these questions. I always love a question that mixes a bit of algebra with some geometry, because I actually always think that that's one of the best ways in which you can really see what's going on. It's one thing to look at equations being multiplied together, but when you see it geometrically laid out, it really gives an image, a visual representation to go along with it. Now, this is what I like about this question. So, it says here, the area of a square ABCD is 10 centimeters square. So we know that whatever this side is, multiplied that by this side, has to give an answer of 10 centimeters squared. That is the formula, after all, of a square. In fact, it's why we even call square numbers that are multiplied by themselves, because you actually have an instance where one side is being times by itself, because actually in a square the sides are equal in length, and so it is just the same as multiplying a number by itself. So let me get rid of that. So in other words, what we notice, by the way, is 3 centimetre plus x, 3 centimetre plus x, they're both actually the same, and they should be the same because it's a square. So we can actually write this in terms of powers. So we can write 3 plus x squared. That's how we can write it, and that equals 10. And that the reason for that is, remember, the area of a square, let me just write a square like that, that's how I like to do it, equals the base times height. The base is here, that's 3 plus x, and the height is again 3 plus x. So there's the little proof for that. Then we want to expand the bracket out. Now, for a lot of people, they would rather write the bracket out in a way which separates the brackets. So 3 plus x, 3 plus x equals 10. Now, remember, you cross multiply when you expand the bracket. Some people even say use the method called FOIL. That's to say you've got the first, outside, inside, and last. So the first ones here is the 3 and the 3, right? That's the first. So that's 9. Then you want to plus the outside, which is 3, add 3x. So 3 times x is going to give 3x. Then you do the inside, which is x and 3, which again gives 3x, as expected. And then you do the last, so that's x times x, and that's x squared. And remember, it still all equals 10. Next thing you want to do is tidy things up a bit. Simplify what's on the left-hand side of this equation. And that's going to be x squared, right, from here. So I'd always say, actually, when it comes to simplifying, start with that which has the highest degree, the coefficients with the highest degree. The coefficients of x with the highest degree, in this case, that's x squared. Next, you go down to x to the power 1, which is just x. So these are these ones here. And you have 3x plus 3x, which is going to give us 6x, and then plus finally 9. By the way, for all you mathematicians out there, this is a coefficient of x to the power 0. Anything to the power 0 equals 1. So behind the scenes, that's actually what you've got, but obviously you don't need to write x to the power 0 because it can be simplified to 1. So 1 times 9 is just 9. Anyway, enough of that. This all equals 10. We now need to simplify, well, we need to solve for x, and the way to do that is to first subtract the 9s from both sides. So we're going to have x squared plus 6x equals 1. So I've taken the 9 from 10 and the 9 from the left hand side. And then we want to factorise the x. We want to factorise the x. How are we going to do that? Well, we take x out as a factor. So we say x, then that's going to be, well, x divided by x squared is x. X divided by 6x is 6, and then that equals 1 still. Now, what we have here is an instance where I've done something wrong, and that's what... Okay, I've got a minute. Okay, so what we actually have to do, my apologies, is we have to get it all equal to 0, obviously, I'm sorry. We have x squared... Oh, that's not the best pen in the world, is it? So we have x squared plus 6x, and that's going to be minus 1 equals 0, right? Because that's what we're going to do. We're going to factorise this. Okay, let's just get on with it. And that's going to equal 0. So we need to think of two factors that multiply together to give 1, but plus or minus to give 6. Now we can all easily think of something that does that. 5 and 1. We can have plus 5. No. 3 and 2. No, 1, 3 and 1. No, hang on. Okay, I've worked out the problem. I forgot I was doing a GCSE paper. I am used to doing A-levels so much that would actually involve me solving 4x. The question doesn't even want us to do that. The question just wants us to express this as that. So all this step that I'm doing when I'm trying to actually find the value of x is not even wanted. All does it want you to do, right? So after you've expanded this out, in fact, let me get back to that. So we've expanded that out, right? then what we need to do is just say, okay, well, we have x squared from there. Let me get the blue ink back. X squared, yeah, plus 6x, because they both add together here. Again, we have plus 9 equals 10. Now, we want to have it so that the right hand side equals 1. And we can easily do that. We just subtract 9 from both sides. So we have x squared plus 6x equals 1. And actually, there you go, there's your answer. That's what it looks like. As I say, I was just stuck in the mode of trying to solve for x, really. You know, I would have been pulling out the quadratic formula at that point. Anyway, let's move on. So, here we go. This question looks pretty interesting now, doesn't it? So this rectangular frame is made from 5 straight pieces of metal. The weight of the metal is 1.5 kilograms per meter. Work out the total weight of the metal frame. So, the approach for this really is to actually work out the length of each side in meters and then times the sum of that by 1.5. Now, obviously, the first some of the sides are dead straightforward. You know that because it's a rectangle, that this opposite side here will also be 12 meters, and this opposite side here will also be 5 meters. But what you don't know so simply is what this here is going to be. But we have a little formula, courtesy of Pythagoras, to work that out. We know that when we have an hypotenuse of a right angled triangle, the hypotenuse squared equals the base squared plus height squared. And so that's what we're going to do. We're going to say h squared equals 12 squared plus 5 squared, which equals 144. Now, you want to know the square numbers from 1 to 13, right? I say 13 because 169 is a Pythagorean square. It gets involved in a Pythagorean square triplet, really, and so it's actually a very handy one to know. And this is actually the classic case of that. So know your square numbers, learn them, memorize them. Don't have to think about them, don't have to calculate them. They come off the top of your head because you've just learned them all from 1 to 13. And we have 12 squared, which is 144, add 5 squared, which is 25, and this adds up to 169. Now, if you've learned what the square of 13 is, then you'd know that the square root of 169 is 13. It's the inverse. You're doing the opposite of what you had done to get it to 169. So that means that the hypotenuse, so we're having to square root both sides, so square root both sides, and we get h equals the square root of 169, which I just mentioned is 13. So that's what that is, that's 13. Right, 13 meters. Now what you do, you add up, obviously you're going to have to then add up all the pieces of metal, right, so you know how much there is in meters, right, okay, so let's do that. We've got 13, add, now we have 2 lots of 12 plus 5, so this is actually equal to 13 plus 2 lots of 17, 2 lots of 17 is 34, and then that equals 47 meters. That's how much, by the way, metal we have. That's how much length in metal we have. Now that's important because we then also know that the weight of the metal is 1.5 kilos per meter. And when it comes to finding the weight, all the weight will equal the length times the weight per meter. Weight per meter. Or weight per length, you might say. So we're going to say the weight equals the length, which is 47. We know the length is 47. That's how much metal we've got in total. And we're going to multiply that by 1.5, or as I like to write it, 3 halves. Yeah, 3 halves, yeah. 47 times 1.5 is 70.5. Now, I don't want to just have done that on a calculator, really. That's a bit embarrassing, so I'm actually going to show you how else you can work that out. I always say the first thing you want to do is normally, right, I would say divide by the denominator and then times by the numerator. But given that 2 doesn't go exactly into 47, you may find it just easier to multiply by the numerator and divide by the denominator. And that's how then I'd approach this. I'd say 3 times 47. Well, we're going to have 120 add 21, which equals 141. And then you want to divide 141 by 2. Well, what? Now, a quick way of doing that is to say, well, what's 140 divided by 2? Well, that's 70. But then we've got the 1, so what's your half, which is 0.5. And then there's the answer, 0.5. And remember, well, see, this is the GCSE makes it all too easy for you guys these days, because in my day, you'd have to know to put the unit yourself. But no, here they give it for you anyway. So here we go, 70.5. So let's have a look at the next question. And that's the answer, 70.5 kilos. So, next question. The equation of the line L1, so we have line 1, is y equals 3x minus 2. And the equation of the line L2 is 3y minus 9x plus 5 equals 0. And show that these two lines are parallel. Now, in instances where, now remember, the general equation for a straight line is y equals mx plus c, where m is the gradient and c is the y-intercept. That's the y-intercept. Now that's important to know, because in instances where we want to show that two lines are parallel, we don't need to bother about the intercept. Wherever it crosses the y-axis is irrelevant to whether the actual lines are going in the same gradient, let's say that are parallel. Now lines which are parallel will have the same gradient. Okay, now that's so all we now need to do. Now conveniently, this line L1 is already in this easy to look at form. Now this form is also a good way of writing the equation of a straight line, because it tells you two crucial bits of information about it. It tells you the gradient and it tells you the y-intercept. Now this one here isn't in that form, so that's what our job is. Our job here for line L2, so for L2 we have to rearrange the line, well, rearrange it such that we can put it in the form of y equals mx plus c, and then determine whether the gradients are parallel or not, or the same or not. So we have 3y minus 9x plus 5 equals 0. Well, what do? Well, we have to obviously get the x term and the constant onto one side of the equation. To do that, we're going to have to say 3y. We're going to plus 9x on both sides, so that's going to cancel out that. So we're going to get equals 9x, and we also want to minus 5 from both sides to cancel out that. So that's going to be minus 5. Then we want to divide 3. We want to divide it all by 3. Okay. So we're going to have, well, 3y divided by y is going to give you y. 9x divided by 3 is going to give you 3x. And at this point we could actually stop, but let's be comprehensive and thorough. We're going to have 5 over 3. Right? We can just write it like that. What we've identified now is that the gradient here is 3. We also know that from line L1 the gradient here is also 3. They're the same. Now that also means that they're parallel. So also I'd write then after that is say, I'd say the gradients are the same. Put in brackets 3x, and then conclude, therefore they are parallel. Boom. Okay, so obviously I've been messing about through this before. I'll obviously just upload this part of the video for now. If you're interested in this video and want to see more, then let me know, and I'll show you how I did all the rest of this. I'll go through it all, really. Yeah, go through it all. It was a decent GCSE paper, you know, decent one. Okay, well, I hope so far that you've found my explanation pretty straightforward. See you next video.